Hi, in a recent video I looked at the Badger2040 from Pico-W and the opportunity of an RP2040 processor with an e-ink display. In this video I want to return to the products and look at the Badger2040W, which brings Bluetooth and Wi-Fi to the e-ink displays. I've looked at the display side of the device in some detail previously. In this video I'm going to deep dive into power management on the Badger2040W. I previously showed a Badger2040 dropping to 2 microamps power draw on hibernation. Can I do the same trick with the Badger2040W? Then use the onboard real-time clock to update the screen once a minute and hibernate in between. Could we use this sort of power management in our Pico-W projects? I'd like to hear your thoughts on these boards and the power management options in the comments below. Please do like the video and subscribe. It helps motivate me and others find this video. The Badger uses the same e-ink display as the Badger2040, so a 2.9-inch display with 296 by 128 pixels, a format that works for a small display or identity badge. Unlike the Badger2040, the board isn't a new RP2040 board. The RP2040 processor comes from having a Pico-W soldered on the back. This is supported with some power management and a real-time clock. Like the Badger2040, there are C++ and Python libraries. There are no specific examples of a C++ usage of the Badger2040W I could find from Pico-W, which is a shame. The front of the Badger-W looks the same as the Badger. In addition to that e-ink display, you also have 5 buttons on the front. These are pull-ups to 3.3 volts when pressed. The switch is organised into 2 sets of A, B and C below the screen, plus up and down buttons on the right hand side. There's also a white LED that can be controlled on the front, though interestingly the white LED is on a different GPIO pad from the Badger. On the rear of board, things start to look very different from the Badger, as we have a Pico-W. There's a reset button. The main connection to your own electronics or modules is via a QWST socket. The micro USB connection on the Pico-W is used as one power option for communication and programming. The board is set up to be powered from a battery using the JST PH connector. Unlike the Badger2040, there are no solder points broken out, though we have all of the Pico-W pins if you want to tap them. Tapping into the SWD port, if we wanted to debug our code, would be very hard. There are some tiny resistors near the top of the SWD port, which are too easy to catch when soldering on the top of the board. To power the device, we have the option of battery or micro USB based power. Battery power between 3 and 5.5 volts. Although you can use a LiPo battery to power the device, there's no charging or power management behaviour for such a battery. It's really designed for common or garden battery packs. You can buy these with battery boxes for 2 AAA batteries as one option. The main connectivity off the board is via the QWST port. This will give you connectivity to an Adafruit, Pico-W and other standard modules without any soldering or lead making. Of course, we are not limited to physical connectivity. We have the Pico-W and therefore the full connectivity stack for the CYW43, so Bluetooth or Wi-Fi connectivity is possible. Some careful power management of these will be needed if you're using battery though. The board is set up so it can run dual power, so battery can act as a backup and this enters via VSys or main power via VBus. These 2 power options can also be used separately. Deep sleep is only available though when on battery. This is because this is all done on external power management logic outside of the Pico-W board. The libraries tries to simulate the board sleeping when it's on USB power, but power usage won't drop as it basically sits there manually looking for a wake-up signal. So how does the Badger2040W do this power management? Well, it has a power control circuit that's taking power from the USB and battery. It is responsible for providing power from the battery and getting out of the way when the user is directly providing that from the USB cable. On USB connection, power is directly applied to the Pico-W, so the power control circuit just disconnects the battery. The wake-up circuits are not used, though those lines are available as separate GPIO pins, so you can detect button presses or the RTC interrupt. We can see this on the schematic, where power from the USB is registered via VBus and turns off Q3, so that the battery power is turned off. In battery-powered mode, then power only reaches our Pico-W if one of the wake-up sources is high. VSys enable is really coming from our wake-up sources. So these are the switches on the front of the unit. These are all pull-up switches, so when active, VSys enable would be pulled up. Of course, we do need to hold something up in order to keep the Pico running. So the hold VSys enable is doing this. Basically GPIO 10 from the Pico-W. So when we wake the Badger by pressing a button, the processor starts and immediately initializes its GP10 and pulls it up, so that the unit remains powered. The other very interesting wake-up source is a RealTime Clock. The power management circuit treats this just like one of the buttons. If the RTC interrupt is raised, then the Pico-W is powered up. We can see the RTC alarm line here, which is the RTC interrupt. The Pico-W uses I2C to communicate with the RTC module. The interrupt from the PCF85063 real-time clock is actually low, so there's a little circuit here to invert it. This gives us a little RTC module and an active high alarm signal when the RTC triggers, so we can use the RTC to wake up our device. With the Pico-W board asleep, we do need an additional 3.3 volt reference to power the RTC and the wake-up sources. So that is the power management capability of the Badger-W. Interesting to analyse and use in our own projects. One downside of this approach is that memory is powered down. A common use case is to hold a state or counter across sleep cycles of the processor. So each time we wake up, we can display the next image in a carousel. Or perhaps some logic or counter to say we go online once an hour. Our Pico-W board is turned off, so we can't hold any local variables. We could assume some state position from the real-time clock though. I think I'd personally like to have an I2C memory module that was actually powered, included in the design. I'm an engineer and complicating things is my life, I suppose. So that was a look at the Badger2040W and a deep dive into how they handle the power management for battery usage. I have a project in mind to test out how usable battery power would be on the Badger2040W. I'm just waiting for some sensors to be delivered. If you'd like me to share the project with you in the future video, do let me know in the comments. Thank you very much for watching. Please like, subscribe and hit that notify button for more content from me. Goodbye for now.